Okay, hey everybody. Welcome to this lesson, which is designed to help you be able to be confident and dominate triangle proofs. This is going to give you the tools that you need to do just that. Before we get going, there's painting going on in the room next door. The fumes are really strong in here as a result, and I hope that doesn't bother you as we go through this. I'm sorry about that. Hopefully I won't faint. Here we go. So when we start talking about congruent triangles, there are several patterns that will help us prove the triangle is congruent. A few of these things are a direct result of the diagrams, and then most of the patterns are a result of what is given about the diagram. So the diagrams are important, and then what is given will be extremely important. So in this set of questions that we're going to answer, the question really is, what corresponding sides or angles can be determined to be congruent for the given triangles? Provide the statements and then the reasons, because there's going to be a proof, there's going to be statements and reasons involved. All right, one of the most common things that you're going to see, or a very common thing that you're going to see, is oftentimes the triangles will share something. They'll share a side or they'll share an angle, so be on the lookout for this. In this diagram here, we got three triangles in this diagram: triangle ABD, triangle CBD, and then the big triangle, triangle ABC. The two that we would be trying to show as congruent are the two on the left and the right. We got triangle ABD and the triangle CDB. Well, those two triangles share a side, right? The two that they share, or I'm sorry, the one that they share is BD. It is in both the triangle on the left, the blue one, and the triangle on the right, the reddish one. So that side, BD, the segment BD of this triangle is the same as the segment BD of this triangle. The reason for that is it's reflexive. A shared side is going to be always reflexive. In this second example of it, we got triangle CAD and triangle DNC. They kind of overlap, which makes it a little bit more confusing, but can you see that they share a side? The CD is the side that is shared. What about in this one over here on the right? Definitely have overlapping triangles. In fact, we got this little tiny triangle here, we got this little tiny triangle here, and then we got these bigger triangles. Well, the two triangles we're talking about are triangles KLE and triangles YLLI. What do they share? Well, they share part of this side, IL, they share part of this side, LE, but that's just part of the side, because IL is part of this side of the one on the left. Anyway, what do they share? Well, they share this angle. The angle L of KLE is the same as the angle L of YLLI. So the reflexive property can get you shared angles as well. So that one ends up being relatively simple. Let's move on. The midpoint. What does a midpoint do? Well, a midpoint makes two congruent segments. So if you know that P is a midpoint of segment MR, and we're talking about, in this case, these two triangles, triangles MPN and RPH rather. Well, if P is a midpoint of that segment, then the two congruent segments are MP and PR, which happen to be sides of that triangle. So, and something that I want us to get into the habit of doing is when we mark that we have MP, the side of this triangle is congruent with the side of this triangle. When that is stated and the reason is given, I want you to mark that that is a side that we have said is congruent. Okay, so every time you have a midpoint, it's going to make two congruent segments. Well, what if the given says that you have a segment bisector? Well, segment bisectors make midpoints. Okay, so if DC bisects segment AB rather, what is the midpoint? Well, D is going to be the midpoint of segment AB. D is the midpoint of segment AB. Why is that? That's the definition of a segment bisector. Every time there's a segment bisector, there's a midpoint. Well, what happens if there's a midpoint? That's what happened over here. When there's a midpoint, it makes two congruent segments. In this case, it's AD and BD. That's a two-step process that gives us that the side of this triangle AD is congruent with the side of this triangle DB. Okay? It's a two-step process. Why is it two steps? The segment bisector makes a midpoint, and then the midpoint makes the two congruent segments. And that happens every time there's a segment bisector. Okay? What about if there's an angle bisector? What does an angle bisector do? It makes two congruent angles. It doesn't make a midpoint, it makes two congruent angles. So in this case, if we have segment TA bisects angle PTC, it's going to make two congruent angles. Which ones are they? These, angle T PA is going to be congruent with angle CTA. These two angles are congruent. Why? It's because that's the definition of an angle bisector. When you have an angle bisector, it makes two congruent angles. That would give you a side. And of course, that's a one-step process that gets you that. So far, each of these things leads us to having a side or an angle congruent in these triangles that we would be trying to be comparing. Okay, let's keep moving. What if you have perpendicular segments? Well, what do perpendicular things do? They make 90-degree angles, right? Okay, so in this case, we're talking about triangles MPN and RPH. Did you see that? I just made that mistake. Anyway, I didn't have the H's there. H. Actually, why don't you put a ha right here, right there. Ha. I forgot the H. So if we got these two triangles and we have perpendicular segments, MR is perpendicular to MN, MR is also perpendicular to RH. What do perpendicular segments do? They make 90-degree angles. So this angle here, angle M, we can call it angle M because it's the only angle at that vertex, and angle R are both equal to 90 degrees. That's the definition of perpendicular. That does not say that those angles are congruent. They're both equal to 90. Well, if two things are equal to the same thing, then they are equal to each other. We can say that angle M is equal to angle R. What is it called when we switch that around? That's called substitution. So yes, we have these two angles that are congruent, but when we have perpendicular segments, it's a two-step process that makes those congruent angles. Okay, so now we can confirm that this angle of triangle MPN and this triangle of triangle RPH are congruent. Okay, what happens if we have parallel lines? Well, if we got parallel lines, then usually 99% of the time it's going to make alternate interior angles that are congruent. Okay, so here we got these two parallel segments, TP and WR. Well, if they're parallel, that was given. If it's parallel, then we're going to have parallel line, transversal, parallel line. Angle T is congruent with angle W. And we got another set. We got another transversal, parallel line, transversal, parallel line, and angle P is congruent with angle R. The reason? If you have parallel lines, alternate interior angles congruent. If you have parallel lines, it's a one-step process that leads you to having congruent angles. They won't always be there won't always be two congruent angles. Sometimes there's only one. In this case, if it's a bow tie or an hourglass type shape like this, it will be two, but it won't always be two, but there will almost always be alternate interior angles that are congruent. All right, this one's probably the trickiest of the lot here, this segment addition piece. What makes it tricky is we're talking about triangles ABF and triangles EDG, which overlap right here. They share some space. So let's talk about what happens. Well, given here is that AG, segment AG is congruent with segment FE. That's key to making this work. Because what we're going to end up showing here is that segment AF, which is part of triangle ABF, is congruent with segment GE, which is part of triangle EDG. Now, this is a multi-step process that happens here. Well, here's the deal. Segment AF and segment GE share this other segment, segment GF. So we're going to have to add it in there. So we got that. We're going to be working our way to showing that AF is congruent with GE. So here's how we start this. We go that GF is congruent with GF. This part of segment AF is going to be congruent with this part of segment GE. Why? Because it's the same segment. GF is congruent to itself. Okay. The next thing we're going to do, we're going to remember that in the given it said that AG was congruent with FE. Now we did this back in the day, but what we said was if you add two things that are congruent, then you get more things that are congruent. So we can take AG plus GF will be equal to GF plus FE. These two things added together will equal these two things added together. If these two things are equal and these two things are equal, we can add each of them to get equal things. That's called the addition property of equality, addition property. okay? Now, with what we've said over here, we have not even made mention of segment AF and segment GE, the things that we're trying to show are congruent. So that's where this comes into play. How does AG and GF apply to segment AF? Okay, this part and then this part put together make segment AF. So that's segment AG plus segment GF is equal to segment AF. And likewise, segment GF and segment FE make up segment GE. That's the segment addition postulate. Now, the whole purpose of this is to show that AF is congruent with GE. Well, here's what we got here. We got AF is congruent to these two things. GE is congruent to these two things, which are equal to each other in the line above. AG plus GF is equal to AF. GF plus FE is equal to GE. They're equal to each other, so AF is also equal to GE. That's a process of substitution. So this is a four-step process that allows us to say that we have, finally, a side of the blue triangle is congruent with the side of the red triangle. But it took us 4 steps to actually make it happen. That's the longest one. Okay, we'll practice it, but these are the steps that you're going to need to learn and follow. The other long one is this exterior angle linear pair deal. If we're talking about these two triangles here, we got this, if we have these two angles on the outside are congruent, we want to show that these angles on the inside are congruent. Okay? So here's how we're going to do it. This was given. We're going to say that TEN plus NES equals 180, and TEI plus IAS equals 180. That's a linear pair. Okay? They form a straight line here together. These are actually exterior angles of that triangle, of course. Because they're both equal to 180, both those things are equal to each other. That's called substitution, like what we've seen a couple times now. Here's the deal. If I'm trying to show that these two things are congruent, NES and IES, they're both on either side of the equal sign. I've got to get rid of these two things. It would help if we had something that was the same on both sides. Well, can we make this TEI equal into a TEN? We can, because, oh, hold on. My bad, this whole time I had the wrong thing there. TEN is congruent to TEI was the given. So can we change this TEI and make it TEN? Well, sure we can, because they're equal. And so that's what we do. That's called substitution. Now we can subtract, because we have the same thing on both sides of the equal, to get what we need to show that we finally have an angle that's congruent. How many sides are there in this one? There are, how many steps? 1, 2, 3, and 4. The last one, well, maybe it is kind of least. It's simple. If you got two triangles that share a vertex like this, you got vertical angles. That's all there is to it. The only thing you have to be really careful about is this. You can't say angle N is congruent to angle N. You have to say angle TMP is congruent to angle WNR. Those two angles are congruent here. Okay? Happens every time. And we'll use these tools to build up to have congruent triangles all together. But these are things you got to know. All right. Lots of stuff going on. Get some rest.